Very good morning to all of you. Today we are going to take an example and see how the error syndrome S helps in correcting error in a block code. So we are considering a block code of size 7, 4. So N is 7 and K is 4. It needs to be generated by a generator matrix. So let's assume that the generator matrix here is also 7 corresponding to the 7-4 block code. It has to have two parts. One is the identity matrix of size 4, another is the parity matrix of size 3. So we have this thing. Let's write down the identity matrix, which is going to be same for this size of a code. This part of the generator matrix is going to be the same for all the codes of this size. And let's write down the parity matrix. That is the unique part, and it is different for individual codes of this size. Now we know that the parity check matrix H for a given code is composed of this thing, this parity matrix. So step 1 here is find the parity check matrix H, and H is given by, we have already discussed this before, transpose of this parity matrix and appended with the identity matrix of size n minus k. So n here is 7 and k is 4. So we have an identity matrix of size 3. Let's write it down, calculate it directly from this generator matrix. So let's transpose this part of the generator matrix, the parity matrix. Let's transpose it. So we will have 1, 0, 1, 1. Let's make the partition here. Okay, and then 1, 1, 0, 1. We are just transposing this p part. Then we have 0, 1, 1. Okay, after that we are going to have a identity matrix of size 3. Sorry, it has to be 0, 1, 0 and 0, 0, 1. So we have this complete H, or the parity check matrix. Now step 2 is to find the code vector C. Okay, and C is given by D into G. G we have here, we need to assume a message block D. Let the message block D be 1, 1, 0, 1. For this message block, the code is given by its multiplication from the generator matrix. So let's multiply D with G. So C equal to DG will yield you this 7 element vector 1, 1, 0, 1 and 0, 1, 0. So we have this code vector corresponding to this message block D. Now we have step 3, find the syndrome. So the question here was how to demonstrate that the syndrome S detects and corrects an error. So in order to do that, we need to first calculate the syndrome S. So this S is given by, we have discussed it in the previous lecture also, C multiplied with the transpose of the parity check matrix, HT. So C we have here, we need to multiply it with the transpose of this HT. We need to multiply with it with this. Okay, after taking transpose. So let's do it. and we will find that it is going to be a 0 vector. So this, what does this mean? This means that if the third bit from left of the code vector suffers an error in transmission, the received vector R will be R is equal to 1, 1, 1, 1, 0, 1, 0. And which is equal to C added with the error vector E. And the syndrome of R is S is equal to R multiplied with H T. Now remember, we have assumed that the third bit from left has suffered an error in transmission. So a 0 which was initially there has become a 1. So initially it was 1 1 0 1 0 1 0. Third bit from left has suffered an error in transmission and it has now become 1 1 1 1 0 1 0. So this 0 at this position in the code has become a 1. Now the syndrome is S is equal to R multiplied with H transpose. Now S here, I'm going to write it here now. S is equal to R. R is a corrupted bit stream. Third bit has been corrupted. We are assuming for the sake of simplicity that only one bit has been corrupted, 0 1 0, and which has to be multiplied with a transpose of parity check matrix. So 1 1 0, we have 0 1 1, we have 1 0 1, we have 1 1 1, we have 1 0 0, we have 0 1 0, and the last row is 0 0 1. This is the transpose of parity check matrix. So verify that this is indeed the case. So it has to be 1 0 1 1 1 0 0. So it is 1 0 1 1 1 0 0. It's correct. So S has been multiplied with HT, and this multiplication will yield you a vector of three elements. And these three elements are 1 0 1. So we also know from the previous lecture that this S is equal to E into HT. E is the error vector. So E is what? E is error vector. So it means if we compare this S with the rows of HT, that particular indexed row, that particular index bit has suffered an error in transmission. So 101, let's find 101 in HT. Index number 1, no, it's not present. Index number 2, it's not present. Index number 3 matches with this S, value of S. It means the third bit from left has suffered a corruption. There is a corruption in the third bit from left, and this will be corrected by comparing S with the rows of HT and correcting the ith received bit if S is equal to the ith row of HT. When the syndrome vector S is 0, it is concluded that no error has occurred. So this S has to be non-zero. First of all, in this case, in this example, it has come out to be 101. So syndrome vector has to be 0 to conclude that no error has been occurred. Okay, now let us assume that two errors have occurred in the transmitted word in MSB and third MSB position. So I am now clearing this canvas and I am again going to take a example of 2-bit corruption. Assume two errors. So one in MSB and second in third MSB. So there are two errors that has occurred. So C is equal to 1101010. What will be R if there is an error in 1 and third MSB? There will be an error here, so 1 will convert to 0. No error here, but in the third there is another error. In fourth it's correct, in fifth it's correct, in sixth it's correct. So every other bit is correct. There are error in this bit and there is an error in this bit. So C has become R here. So let's calculate S is equal to what? S is equal to R into HT is equal to 0 1 1 1 0 1 0, and let's multiply it with HT, which is 1 1 0 0 1 1 1 0 1 1 1 1 1 0 0 0 1 0 and 0 0 1. So let's multiply it. We will get a 2 3 element vector. So we have 0 1 1. So let's try to find out 0 1 1 is there. Yes, 0 1 1 is there in the second bit, but the syndrome 0 1 1 matches with the second row of HT, resulting in conclusion that a single error has occurred. Going by this example, we will conclude that single error has occurred in second bit from left. But is it the case? No, this is not the case, because we have deliberately done error in this and this bit. So this assumption is wrong. It means that this syndrome method is capable of correcting only a single error. Thus, it can be concluded that double errors cannot be corrected by above code. Similarly, it can be shown that more than two errors also cannot be corrected by the above code. Hence, this particular methodology is a single error correction scheme.